All right, let's talk about forces. So here's how you can use this video. Throughout the video, there's going to be text highlighted in green. If you're using this to take a notebook, this is what should be in your notebook. Now, there's also going to be some questions throughout, like practice problems or questions for you to consider. Those are going to be written in blue. Now, also throughout this video, there's going to be two codes. One is a verbal code said by myself. One is a written code that will show up on the screen. They can show up in any order, so pay attention. All right, let's get started. So let's ask this question. What is the difference between mass and weight? So here is just the difference. I'm going to give you the definitions of each and just little bullet points. So mass is the measure of the amount of matter or stuff in an object. Like what makes up that object? Now, it's measured in kilograms. It does not depend on location. I'll go over this a little bit later. It is closely related to inertia, cannot be measured directly. Now, it is a scalar quantity, which means it's only magnitude, no direction. Now, weight is the measure of the amount of the force of gravity on an object. So it's a force. Now, it is measured in newtons, represented by a capital N. It can change with location. It is closely related to gravity, can be measured directly with the scale, and it is a vector quantity, meaning it has both magnitude and direction. So here's what I mean by this, right? Like if we look at location, mass is just the amount of stuff. No matter where you are on Earth or in the universe, the amount of stuff that makes up you is not changing, right? Now, the force of gravity will, because on different planetary bodies, the force of gravity or the strength of gravity can change, right? So you can see this little box, 2 kilogram box, no matter where it is, whether it's on Earth, the moon, we're out in deep space, it's still 2 kilograms of mass, the amount of stuff, right? Now, the weight, the force of gravity pulling on it can change based on where it is. So if we look down here, like this would be like an astronaut. Hey, if you're going from the Earth to Mars, no matter where you are, that does not change, right? But the weight, the force of gravity will. And you can see I put this picture of myself at the Hayden Planetarium. They had scales that would show you what you would weigh on different planetary bodies. This one was on the moon. You can see here I would be about 30 pounds. But if I went from Earth to the moon, that would not change the amount of stuff that makes me up, but it would change that force of gravity. So here's how you can calculate weight, right? Let's see here. So the magnitude of weight, that's what we're going to be concerning ourselves with, is given by this equation, right? F of g, or force of gravity. And like, don't get confused about that. That lowercase g just tells me what type of force it is. We're going to learn about different forces, but that is what we call weight, the force of gravity. It's just like I could be solving for x or y or z or whatever. It's just F of g. The force of gravity is the mass times the acceleration of objects. And we represent that with g, right? That's sort of like just the magnitude. Like how much does that object accelerate at that surface? And you can see, let's see, on Earth we use 9.8 meters per second squared. That's the acceleration. That's the strength of gravity on Earth. And the weight force is direction. The direction of the weight is always going to be downward, right? So when we use this calculation, yes, technically it's downward. When we talk about putting other forces, it's always going to be pointing downward. I don't want to confuse us with like negatives and like whatever. It's always going to be pointed down toward the center of Earth, right? So it is a vector quantity, we'll always that, but when we're calculating it, we're going to calculate the magnitude of just the magnitude. That's what we're going to be talking about, right? So yep, on Earth, it's always going to be pointing downward. And actually, interesting fact, remember when I said it depends on location? Yes, it is 9.8 meters per second squared. That's kind of like the average. It does change based on where you are on Earth. The farther you are away from the center of the Earth, the less gravity is. Now, it's not going to make that much of a difference, but yeah, if you go from downstairs to upstairs, technically gravity is going to be a little bit less, but overall, the average, like on Earth's surface, 9.8 meters per second squared. So we're just calculating the magnitude force. We're just going to say it's positive, but we have to know that it is downward. And we'll talk about how we can denote that a little bit later. So now let's get some practice calculating weight and using these problems. So here are some problems, right? And we'll just start off with an easy one, right? Backpack has a mass of 12 kilograms. Calculate the magnitude of the backpack's weight on Earth. State the direction of the weight force. We know the weight is going down. So what I'm going to do for these problems here, I just have 3 problems here, and these are going to be for each of the variables. I'm just going to show you how to get the equation using this triangle and set that up, and I'll show you how to do that. So the second one is a box experiences a weight of 196 newtons on Earth. Calculate the mass of the box. Now, this last one is an astronaut standing on the moon has a mass of 75 kilograms and a weight of 120 newtons. Calculate the gravitational strength on the moon. So before I set this up, I'll go ahead and give you that verbal code. It is 856. Say that again, the verbal code is 856. So let's take a look at that first one, right? So I'm going to state, let's see, I want the weight, right? The magnitude of the weight. I know the mass, and I know it's on Earth. That doesn't really need to be stipulated, right? But the gravitational strength, that is going to be 9.8 meters per second squared, right, on Earth, right? Now, the equation, well, I gave that to you right here. So that's going to be it, right? The force of gravity equals mass times that strength of gravity. Good. So you can calculate it that way, right? Now, let's do number 2, right? So I want to know the mass now. I know the weight, and I know it's on Earth, so that's my gravitational strength. So what you do is you cover up mass, and the equation to find the mass equals the weight, which is force of gravity, divided by that gravitational strength. Now the last one, this one is if I need to find the strength of gravity. So the gravitational strength, right? I'll just underline that there. So I know the weight, and I know the mass. So I cover up gravitational strength, and I get gravity equals, well, the weight divided by the mass, right? So I'll go ahead, if you want to pause that, you want to practice doing these problems, you can go ahead and do that. Let me perfect, there we go. All right, so now let's move on. What forces are acting on you right now? So unfortunately, it's not the force from Star Wars, but we learned about gravity, but there are other forces, and there's some that you might easily overlook. So when we're talking about force, a force is a push or a pull in a given direction. Now it is a vector quantity. It's right there in the name, right? It has a direction, which means it has both magnitude and direction. Now the unit is Newton. We already learned about that with weight. It is the Newton. So we represent the force by a line with an arrow to indicate the magnitude and direction of the force. We'll get to that later. But real simple, right? A force is just a push or a pull in a given direction. Now, these are the types of forces that we're going to concern ourselves with. Now, these aren't like the fundamental forces of the universe. These are just the macro level forces that we can divide forces into, right? And there's 6 of them. Now, it's the force of gravity. We already learned about that, right? Or the weight. Now, the normal force, F of n, that's a perpendicular support force. I'll get to this one later, right? The applied force, this is the force from a person or object onto another person or object that attempts to change the motion, right? So just a push or pull from another person or object. Friction, F of F, that opposes sliding motion. Drag, so that's resistance, opposes motion through a fluid. Most of the time it's air. This is like air resistance. And the last one we'll learn about is tension, F of T. So that's force from a rope, string, or spring. Now I've actually seen this one separated into another one, like a 7th force. I've seen spring separated into another one, and that's because there are equations for like springs with spring constants and how much you're pushed and pulled. But just for these purposes, I'm going to combine them into one with tension. If you take a look at this, right? So if you take a look, here are some just quick diagrams of the types of forces here. Now the one graphic I have up there is the normal force, right? Now normal in mathematical terms means perpendicular. It's like perpendicular to the surface that it's on. So if it's on an angle, yeah, that normal force gets a little bit tricky. But think about it this way, right? If you only had gravity acting on you, your weight, you would be falling down, right? Falling down towards the center of the earth, but you're not. Something is stopping you. Right now I'm sitting in my chair. The chair is providing that upward support force, that perpendicular support force. And you can see that the you can see that little graphic here. It's sitting on a table. Well, I've got the weight. Well, the table's supporting it. You take away that table. Well, look what happens. Now I've got gravity. It's accelerating downward. Then it hits the ground. Then I've got that normal force. That's the perpendicular support force. That's the one that confuses people. Now, you can see this little graphic down at the bottom. You can have multiple forces acting on an object at once, right? So you can see that little graphic. Well, hey, it's got the weight. You've got the normal force. Well, there's an applied force. That person is pushing on that object, and then friction is resistance to sliding motion. Probably also a little drag from the air if you get going fast enough. That brings us to our next topic, which is net force. So net force, right, and it's represented by this symbol, right? And it's the sum of all forces acting on an object, right? So I think that's the Greek letter, it's a Greek letter, and that just represents the sum of all forces, right? So if you add them all up, you get the net force. It's not a special type of force. It's not like gravity. It's like, hey, great, I've got one net force. I add them all together. So they can add to each other. So think about pushing a car, pushing an object, right? If one person is pushing in one direction, another person is pushing in the opposite, those forces will not help each other. But if they're pushing in the same direction, the forces help each other. So you can see that up here, right? Now, the direction of the net force acting on an object is always the direction of the acceleration. So if you take a look over here, I've got some examples here, right? So I've got a car. Yeah, the gravity and normal force is acting on it. But I've got like an applied force, or technically friction is what the friction of the tires is what's going forward, but even though it's not sliding. But 5,000 newtons going forward, 2,000 newtons of like air resistance. Well, the net force, I add all the force together, I'm left with 3,000 newtons to the right. That's the direction it's accelerating. If you look at that soccer ball, it's falling through the air. Well, I've got the weight, it's pulling down. I've got air resistance, right? That's 2 newtons. You add them together. My sum of all forces, all the forces, is 3 newtons, and it's accelerating in that direction. And you can see down at the bottom, you can see that this is an example, like, yeah, the net force can be 0 newtons, and this is an object falling through the air. It gets to terminal velocity when the weight is balanced out by the air. It doesn't mean that it's not moving. It just means it's not accelerating. So you can see here that's what's happening in that little graphic there. But anyway, like, yeah, this is just a way to practice it. What is the net force acting on the box, and in what direction? So you can see here, my weight and the normal force, they balance each other out. That's what the normal force does. It balances it out. But you can see it's being pushed with an applied force to the left with 75 newtons, and friction is resisting with 35 newtons. So I add all of them up, and I'm going to get 40 newtons to the left. Right, I add them all up. That is my net force acting on that box. So now that comes into play with what we're talking about here. This is balanced versus unbalanced force, right? So this sort of puts it all together. So once again, these aren't special types of forces, just used to describe all the forces acting on an object. So if a balanced force, if all the forces acting on an object are balanced, then those forces cancel out, meaning my net force is 0 newtons. And that object is not accelerating. That means that it's at a constant velocity or rest. So I put this little graphic of these astronauts in space, right? So it's sort of hard because we're a bias here on Earth about constant velocity or rest. But like astronauts in space, right? If they pass by each other and one's like at rest and one's at a constant velocity, they don't feel that motion. You do not feel constant velocity or rest. Neither one of them could say, oh, you're moving, I'm at rest. I'm at rest, you're moving, right? You do not feel constant velocity or rest. Think about it this way, right? If you're sitting in a car and it's at a stoplight, yeah, you can take a nap, right? I mean, if you're the passenger, you can take a drink of water. But if you're on the highway, if you same thing. If you're going 60 miles per hour at a constant velocity, you can still take a nap. You can drink some water. You'll be fine. But if someone slams on that accelerator or the gas, you're going to feel that motion, right? And that's why I put that graphic down below here, right? If the forces acting on objects are unbalanced, the forces do not cancel out. The net force is not 0 newtons, and that object will be accelerating. That means it's speeding up, it's slowing down, or it's turning, and you can see that guy, you can feel that acceleration, right? Net forces will cause that acceleration, right? So how do we represent forces? So that brings us to our last topic here, which is a free body diagram, right? So a free body diagram, or FBD, that's just how I simplify it, represents the forces acting on a body. So here are the steps to make a free body diagram. First, identify the object or system. You're just picking one, right? Sketch the object, right? Now, it could be a simple sketch. Normally what I do is a box or a dot. A dot is probably the simplest one. You can see here down at the bottom here, there are some drawings of just a dot. I like that, right? Real easy. Now, identify those external forces. So the ones we talked about, gravity, normal, friction, tension, applied forces, drag, whatever. Now then you draw those force vectors. Draw a force as an arrow starting from the center of that object or that point, that dot of application pointing in the direction of the force. So it's going to be pointing out, right? Now, then you label forces and set coordinates. Setting coordinates, that's if it's like at an angle, then you can do different stuff, but just labeling the forces, right? So label each force here, right? So that the top one is probably the easiest one here, right? So you've got applied, or I guess it could be tension because it's a spring, but you've got gravity, normal, and you've got friction, right? That's how you draw a free body diagram. So let's just put this all together, right? So for each scenario given, identify whether the object is accelerating or not, the net force is 0 or not 0, forces are balanced or not balanced, then draw a free body diagram, right? So these don't have any numbers, but like with these, there's 5 scenarios. I'm just going to do the first one, right? And you can practice with the other ones, right? So let me just get the pen out. A box is being pushed to the right at a constant speed across the rough floor. So I look at that and I look at constant speed here. Okay, well I instantly know that it is not accelerating, which means the net force is 0, meaning those forces are balanced. So when I draw these arrows, they should all balance each other out. So free body diagram here, I'm just going to draw a dot here. That's real easy, right? So if it's on a floor, okay, great. I have got gravity, and I'll label it as I go, just for the sake of time. F of G. Well, I've got a normal force. Remember, these are going to be about the same, so I'm going to try to make them about the same. That's my normal force. Right? Now, it is being pushed to the right, so my applied force is going to be this direction. You know what? I'll make it a little shorter than the other ones, just to show you that, just to show you what I mean here, right? So then, this is my applied force. I'll put F of A. Right, there we go. Now, I know that it's traveling at a constant speed. All the forces are balanced out. The ones that say rough floor. So there we go, right? So that one is going to be my force of friction. There we go. Perfect, right? So that would be that free body diagram for that one. Now, go ahead. You can practice the other 4. And I tried to pick some that would do all 6 of those forces that we had practiced. But some of them are moving to the left, moving to the right, up or down, and some of them are accelerating or not, right? So get practice doing that. All right. So just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.